Okay, so we were discussing about the spectral signature or the reflectance patterns, which are very important in the subject of remote sensing. Normally, by recognizing these spectral signatures, someone can tell from a distance uh, about the property of the particular object of interest, and thus satisfying the requisites for a remote sensing environment. Now, uh, let us focus on this slide. So, we are going a little bit deep into the subject. When you see a photograph or a digital photo, nowadays it is very easy to get access to a digital photo. How? Because we have all our cameras, and then by making use of the cameras, you can take a photo anytime you want. So this is also a similar kind of photo which is being shown here. This is what is this? What do you see? What is this animal? Yeah,
So
yeah. What is this animal?
it's a zebra.
Zebra. Yeah. This is a zebra. Okay. So I am trying to explain different resolutions of a remote sensing satellite image. And in that case, I am showing you the face of a zebra. Okay, so this is the zebra. And then if you have an image like this, you can zoom onto a particular portion of the image. That is actually being shown here. So in the screen you see this part is actually being focused and then it is shown here. How do you do it? You simply use the zoom tool. Okay? You know it, how to do. So you take up the photograph for this particular photograph or any other photograph that is a digital photo, and then use even your camera or your laptop to open the photo, and then you start zooming onto the photo. Then you keep on doing this, zooming, zooming, zooming in, zooming in, zooming in, and then ultimately you will come to a point where you will start to see individual boxes like this in the photo. Have you seen this? Have you ever tried to see this thing? So you do one thing today. You take your selfie, okay? And then you start to open the selfie and then keep on zooming on the face. Then ultimately you will come to a point where you will start to observe this rectangular grid or these square boxes. It may be square, it may be rectangular. In most of the cases, it's a square. So we start to see the square boxes. So once we reach this stage, even if you zoom farther, you will not see any different things except the square boxes. So these square boxes are called the pixels of a photograph or the pixels of an image. This is often known as the element I don't know, maybe your chromosome or DNA is known as the element of life. Similar way, this is known as the element of picture. That means this is the primary thing of a picture. Even if you zoom farther, you only will see this thing and you cannot get any other meaningful information upon farther zooming. So why we are talking this thing? Because the size of the square boxes, they influence the amount of information that is being contained in the image. So if you look at this square box, you will see that I have shown you dimension in x as well as in y's direction. This is a two-dimensional thing. That means it has got its length as well as it has got its width. I'm talking about these boxes. So this shape and then this size, actually, as I said, it will determine how clearly you are to observe the face of the zebra. Another thing is that inside this box, you get to investigate anywhere, you will see a similar value or a similar information as long as you are inside the box. The moment you cross from one box to another, this information will change. So that means there is an average value or a common information which is being contained within the pixel or the square box or one particular square box. What is this value? Okay, so in case of a satellite image, this is, remember in our first lecture we said, what does it measure? It measures these three different kinds of energy: reflected energy, or emitted energy, or scattered energy. So, within the square box, when I am talking about satellite image, this will be an averaged value of a mixture of all these three different energies that is coming from a particular place on the surface of the earth. So in some cases, the dimensions are in x direction, it may be 30 meters, in y direction, it may be 30 meters. So you imagine a space of 30 meters long and 30 meters wide. So from that space, you get one particular response of a mixture of three different kinds of energy, which is being recorded back at the sensor on board the satellite. Remember, within this 30-meter area, though there may be a variation in the level of energy which is being reflected, or which may be scattered, or which may be either emitted, when it is recorded, it assumes this energy to be an averaged energy or an averaged value. It may be energy or it may be undulations. Normally, forget about undulations, we are concentrating on energy. So, this is an averaged value of the energy that is being recorded from an area of suppose 30 meter by 30 meter on the ground. Okay, so if we design our sensors in such a way that we are able to receive this energy from a smaller area, maybe 5 meter by 5 meter, then we will notice some changes in our complete picture or complete image. What are these changes? Okay, look at the right hand side of this image. This is the same image which has been captured using camera on board a satellite. On the first image, left hand side, extreme left, top left, the physical size of the pixel is 1 meter by 1 meter. Means in this case we have a physical dimension of 1 meter wide and 1 meter long. It means when the image is being recorded, this information is coming from an area of 1 square meter on the ground. Next image, same area. This information is coming from an area of 5 meter wide and 5 meter long area on the ground. That means 5 multiplied by 5, 25 square meter area on the ground. Third image, pixel size is 10 meter by 10 meter. That means 10 by 10, 100 square meter. That means this one particular box is an average information coming from 100 square meter on the ground. Last one, 30 meter by 30 meter. That means 30 by 30, 900 square meter on the ground. So if you keep on increasing this physical size from which this information is being recorded, or in plain terms, if you keep on increasing the size of the pixel, you lose the total information content. Or reversely, if I say, if we keep on decreasing the physical size, or if we use a smaller pixel to record, we can capture more information. You can tell the difference by looking at these images. When it is 1 meter by 1 meter, you can see a lot of details on the ground. When the pixel size increases, this level of detailiness drastically drops. So, when we are talking about resolutions, remote sensing images, we have to talk about 4 resolutions. This resolution is known as spatial resolution. S-P-A-T-I-A-L, not spatial, okay, not S-P-E-C-I-A-L. This is not spatial. You can, I don't know, but normally it is called spatial resolution. And you write it as space, S-P-A-T-I-A-L, spatial resolution. That is in reference to space, not spatial, S-P-E-C-I-A-L, no, not that. So this is corresponding to the space or the size of the pixel on the ground. So remember, the thing that the gist of this discussion is that the moment this resolution becomes smaller, we can store more information in the image and vice versa. So today when you take your selfie and then you open up the image, try to zoom it farther and farther and farther, and then ultimately you will see the similar kind of boxes. And then if you look and investigate the size of this particular boxes, you will arrive at different numbers. It is true for a satellite image as well as it is true for an image that has been captured with any ordinary camera. Okay? And remember, these square boxes are known as picture elements or pixel. P-I-X-E-L, pixels. So this is the first kind of resolution we have to say when we are discussing remote sensing images. And there is another information resolution which is important. Okay, so this is the sorry, this is the same example, but with a different area. So what is this? What do you notice here? Can someone tell me? What do we see here in the screen? Okay, by the way, I am sharing you the link for your attendance here. Oh, someone is having problem listening to me. Can you hear me? Can you hear me?
Oh,
Yes or no?
yes, sir.
Okay, good. Oh, in the chat, I have shared you the link for your attendance. Okay, so discussing our spatial resolution. So let us see this image and then tell me what this image is actually. This is a satellite image, but what actually this looks like? Yes. What do you think these are? Hmm? See, you have to answer, otherwise your things will be just like this. I cannot go on speaking in front of the whiteboard. What do you think these things are? Are these animals or what? Why are you so afraid to speak? I don't understand. There are a total of almost 30 students. None saying anything. Yes, Nitu Munisunwal, what are these things? Just tell whatever you see, whatever you feel. That it's not to be correct. I just need an answer. Imagine on your part, can you really keep on lecturing in front of a wall for 1 hour? Communication is a two-way process. Are you really there? Simikolita, what are these?
Sorry, sir, I can't able to recognize what is this.
Okay. Who can tell? Saidul. Kuntaljuti? Kuntaljuti, are you there? Hey, please. I need an answer, eh? Otherwise, I will next class onwards, I will make all of you to just switch on your videos. This thing cannot go on like this. If you don't speak You don't show up your faces. This is a fruitless discussion.
Sir,
You have to have a good connectivity. You show up your faces, otherwise you speak whenever I am asking you something. The answer need not be correct. The important thing is that you answer, you take part in the discussion. That's from the first class. I have been putting an emphasis on this thing. This is master's level class. You know, when we were in master's levels, often each other day we have to appear for presentations. And you were even reluctant to speak repeatedly whatever I am asking. This is a stadium. Whoever is familiar with sports, this is a stadium. The stadium is being photographed from directly above. If you have this experience of looking at things, whenever you fly, you look down below, you see the similar things. Not only maybe a stadium, but you can make a sensible guess. There are buildings, the roofs where you can see these things. This is a stadium. The green patch is actually the carpet or the grass. The surrounding, this is the arena where people sit and then they attend the sport. Okay, so the point is, the first one, if I show you the picture which is down below, this picture, you probably will not be able to tell what this thing is. But if I will show you this picture or the picture in the extreme left on the top, if you are familiar with sports, you should be able to recognize that this is a stadium. Why? Because forget about whether you play sport or not. In the first picture, the spatial resolution is 1 meter by 1 meter. It means the physical dimension from where this information is being extracted or coming is much smaller than the one or the rest of the others. The point is, if you are using a smaller spatial dimension, you increase the information content. You increase the information content means things become clear to your eyes. You will be able to tell. In the extreme right corner image, I understand even a sportsman, he or she will not be able to tell what this thing is. The moment we are decreasing the spatial resolution, things are getting clearer. So this is a similar example as the one shown before, which tries to highlight the fact that a change of spatial resolution affects the clarity of the image or the information content in the image. Remember, we are into the subject of remote sensing. These things we have to discuss. So when we were talking about resolutions, then next in the list is known as the spectral resolution. First one is spatial, second one is spectral. What is a spectral resolution? Okay, so let me put it in this way. Everyone nowadays, they do have a camera, Either you have a digital camera or DSLR, or maybe you just use your phone or the camera to take a photo. In any of these cases, when the camera is used to take photographs, particularly the colored photographs, it uses three different sensors. Either it is the blue sensor or the green or the red. So with a combination of these three sensors, you see the different colors that are normally shown in a photograph. In case of a black and white photograph, this is either black or white. In a colored camera or colored photograph, we have three sensors, normally blue, green, and red. So if you're talking about spectral resolution, it is an indication of how many sensors are there in the camera or in the satellite. Okay, and what are the corresponding ranges of wavelengths which are used in order to capture the information. For example, in a satellite known as Landsat 8, remember we discussed Landsat 8 in the first lecture. This is the satellite which was flown by the United States in 1972. So in 1972, United States started this Earth observation with the launching of Landsat series of satellites. And in the Landsat 8, which is the current Landsat, it has got 11 various sensors, as you can see it in the list. So the first sensor, or the first band, also known as the band, has a wavelength starting from 0.43 up to 0.45 micrometer. So that means that particular sensor is designed to capture information or capture the amount of energy. It's three kinds of energy that is being reflected or emitted or scattered in the range of 0.43 to 0.45 micrometer, okay, or 430 to 450 nanometer. So that is the spectral range for band number 1. Then it has got another band which is known as band number 2 or sensor number 2, which is also known as the blue sensor. And then this blue sensor is designed to capture information starting from 450 to 510 nanometer. So how many sensors in total the satellite has actually is an indicative of the spectral resolution. In this case, Landsat 8 has 11 different sensors. How many sensors normally our handheld cameras they have? We have 3 different sensors. If you are having an expensive camera, or if you are having a camera that can capture in the night time, probably you have an additional band or sensor, maybe in the near infrared region or in the thermal region. So the night vision cameras, they can capture somebody from a distance by sensing the temperature. That is a thermal sensor they have. See, here also you have band number 10, which is a thermal sensor. Okay, so in total 11 sensors, and that is an indicative of the spectral resolution of Landsat 8. On the other column, you see that this resolution in terms of meters is an indicative of the earlier resolution of spatial resolution. That means for band number 1, the spectral resolution is 430 to 450 micrometer, and then spatial resolution is 30 meter by 30 meter. Similarly, for all of the bands, you have these ranges and then these resolutions. See, we cannot escape this part when we were talking about remote sensing. Though I understand that probably this is a bit difficult appearing to all of you, but I'm trying my best to simplify it in the term that may be understandable to all of you. So that is why I'm constantly asking, if you have a question, please ask. Or otherwise, you just look into the videos that I'm going to share and try to understand whatever is being discussed. Because you need to have a rudimentary grasp of this particular things which have been told here. If you are interested in taking this subject. Okay, the next in the list is known as the radiometric resolution. Okay, radiometric resolution is the third kind of resolution whenever we are talking about a satellite image. Or it may be any image. What is a radiometric resolution? In plain terms, it is the fineness of the scale with which the data is being measured, or the property of the objects are being measured. For example, on the left hand side of the screen, you are using a sensor which can capture a 2-bit information. On the right hand side of the screen, it is the same place, but we are using a sensor which can capture information of an 8-bit scale. So what is a 2-bit scale? What is an 8-bit scale? If you are into computer science, little bit, 2-bit information means 2 to the power 2. 8-bit means 2 to the power 8. So if it is an 8-bit scale, 2 to the power 8 is 256. That means you have got 255 different levels or different houses where you can store this information. If it is a 1-bit scale, it can be either white or it can be either black. Because why? 2 to the power 1 is 2. That means the available houses to store this information in the hard drive, 2. If it is an 8-bit image, it has 2 to the power 8 is equal to 256. Starting from 0, you will have 255 number of houses, or different levels of grayness which can be associated with the amount of energy that is being reflected from a particular area on the ground. So in a way, it is the same thing. If I ask you to measure the length of a particular house or a room, you can measure it with a very coarse scale, or you can measure it with a very fine scale using a vernier caliper. You can go beyond millimeter or sub-millimeter level. So if you are using a finer scale, your radiometric resolution is higher, or a particular image, if it is being used, a particular image, if it is using a finer scale to measure this information coming from the ground, we can say that the radiometric resolution of that sensor is more, or vice versa. The other way around, we can say that the radiometric resolution is less if the scale with which this energy, which is being measured at the sensor, is really close. I will not ask you anything on this, particularly into this computer science, bit and byte, those things, but just you need to know what is radiometric resolution. Okay? So this is the fineness of the scale. Then last one is the temporal resolution. So temporal resolution is indicative of the amount of time which is being needed once the satellite is rotating this part, and at the moment it is capturing information. Suppose today the satellite is capturing an information or a photograph of this particular area. You can see it on the screen, right? My mouse, I am moving. So because the Earth is rotating like this and the satellite is constantly rotating from north to south, following polar orbit, after how many days it is going to capture this place or take a photograph of this place exactly, that will be the temporal resolution. So temporal resolution is an indication of the amount of time that is needed in order to take or capture the information of the same place on the Earth. Some satellites, if they rotate very fast, their temporal resolution is higher. Some satellites, if they rotate or move very slow, their temporal resolution will be high. For example, in this list, you see that there is a French satellite known as Spot, which takes exactly 26 days in order to capture information on the ground. It means every 26 days after, it will come back and then take a photograph of the same area. Lancet 16 and NOAA and Terra Equamodis, they almost every day. It means their temporal resolution is much higher. So temporal resolution is an indicative of how many days after that the first picture is going to take the second picture in the same area on the ground. Okay, so we stop here for the time being. You have to really search a little bit of information, whatever you can get by Googling, or maybe whatever the references I have given you. Or you can just simply look or view my lectures I'm going to share it today, and then think whatever is being discussed. Okay? And then if you have any doubts, discuss. Do not fear to question. Okay? Are you there? Yes? Oh,
Yes, sir.
Yes, sir.
yeah, good. So, for the time being,